Hey everyone, I'm Kevin Yang, and I'll be interviewing Václav Kuna for today's Tech Talk. I'm part of Origin, which is Northeastern Science and Tech Startup Incubator, and we have two main events: ideation and innovation sessions, and we have Tech Talks. So for the Tech Talks, it's every Thursday at 7 p.m. and we connect with scientists and researchers who have very interesting research to share with us, and we would love for you to tune in every Thursday. So this Tech Talk will be first 30 minutes of Vaslav's presentation to start, and then 30 minutes for questions to finish, including your audience questions. So without further ado, I'll let Vaslav start his presentation.
Thanks, Kevin. Let me, I need to stop you sharing. Let me share my presentation here. Can you see my presentation?
Yeah, it looks good.
So, thank you. Thanks for the introduction. As Kevin said, my name is Václav Kuna. I come from Czech Republic originally, and I just finished, or a few months back, I finished my PhD at Oregon State University in Oregon. And I'll talk about a part of the research that I was involved in when I was doing my PhD. So my main topic was investigation of oceanic transfer faults. But in the last year of my PhD, I got kind of sidetracked on this whale path and using seismic data for researching whale sounds and how whale songs can help us and help us learn something about geology and tectonics. So that's the part that I'll be sharing today with you because it's recently got published and it's kind of a fun project to talk about. So just a few words about how we actually, why we collected the data and what was the main subject of the research. We wanted to study oceanic transfer faults. And oceanic transfer faults are faults that connect spreading ridges. So you are probably all familiar with plate tectonics. And there are three major boundaries. There are the spreading centers usually that are located in the oceans. Then there is a subduction, and then there are something like a transfer fault, transfer boundaries where the plates move along each other. So when this happens in the ocean, they are called oceanic transfer faults, and they are quite short, several hundred kilometers long segments of those faults. And in terms of physics of earthquakes, they are very interesting and quite, because they are quite inaccessible and remote, there hasn't been that much research done on them. So we wanted to study these faults. And the fault that we chose to study was the Blanco Transfer Fault, which is located in the Northeast Pacific, about 100 kilometers or 200 kilometers of the coast to the west of the coast of Oregon and the west coast. So here we have Washington, Oregon, and California states. And there is a small tectonic plate, which is called Juan de Fuca plate, and the Pacific plate. And where they meet is the Blanco Transfer Fault. So this is the fault that we went out to study. The way that we study these faults is, or from the seismological perspective, is primarily by using seismic sensors. So a seismic sensor, the principle is that we have some kind of a mass on a spring, and it's hanging on a frame, or it's attached to a frame. So when the frame is sitting on the earth, when a wave comes, it can be an earthquake wave, or it can be any kind of other mechanical wave, it shakes the frame. And because the mass is quite heavy, the mass stays at the same spot. And, you know, back in the day, it was drawing something on these drums that were rotating. So that's how seismic waves were recorded. Nowadays, it works slightly differently. However, the main principle of hanging mass on a spring stayed the same. So we have these modern seismic sensors that are very expensive, about $10,000 a piece. So, and we also have hydrophones, which are pretty much microphones under that work on the same principle as microphones in the air, but they operate under the water. So we have these two kinds of sensors that we can deploy around the fault and study earthquakes that occur on the fault. So these sensors are attached or are included in these ocean bottom seismic station packets. So these yellow boxes that you can see, those are ocean bottom seismic stations. So they include the seismic station, they include the hydrophone, they include all this like recording things, data storage and everything. So they, each of these get all those sensors. We go out there on the sea and deploy these sensors by simply lifting them on a crane and dropping them over the board at the spot where we want to have them. So we deployed about 54 of them around the fault, and we always went to the spot where we want to have the station. We dropped it over the board and let it sink to the bottom of the ocean. The depth of the ocean where we deploy them varied somewhere between 1 kilometer and 5 kilometers. So there is quite a bit of drift, like there are ocean currents and stuff like that. So the station doesn't sit exactly where you drop it over the board, but it drifts a little bit to the side. And you can communicate with the station, so you can locate where exactly the station is. And once you have done this, you leave the site and you leave the station sitting there for a year, and you cross fingers that it still records the data, because you have no way to contact the station during this period. And in about a year, you come back and you can communicate with the station when you are nearby. You can communicate acoustically with the station, and it releases a weight that is attached on the bottom of the station, and then using its own buoyancy, it rises up back to the ocean surface. And you fish it with like something like a fishing rod, and again you lift it up on a crane and take it back on board. And at that point you find out whether it was collecting the data the whole year, or whether it was just sitting on the ocean bottom doing nothing. Like sometimes something goes wrong, it can be recording, it can be anything pretty much, and you don't know about it until you fish the station and find out what it was doing in there for a year. So it's always a little bit thrilling. But in our research, we were very lucky, and we recovered almost all the stations and almost all the data from the stations. So as I said, we deployed 54 of these stations. So this is a bathymetry, a detailed bathymetry of the fault. You can see that the fault, this ridge is the fault, and also there are some smaller basins like depressions that are tectonically opened in there. So it's very heterogeneous, and it produces a lot of earthquakes. So these white triangles are the stations that we deployed around the fault, and they were sitting there for a period of 1 year from 2012 to 2013. So this is how our earthquake data looked like. So this is one earthquake recording, and altogether we recorded about 8,000 small earthquakes and some larger earthquakes too during that period of 1 year. So we had some interesting results. So you can, if you are interested in this part of the research, you can also look them up and see what was actually the main motivation for the research. But I will not talk about earthquakes anymore, because I found something that got me sidetracked at that time. And those were these weird recordings that they were very abundant. So this is about 1 hour of the signal from one station. So as you can see, there are four traces. Those traces belong to 3 components of a seismic station. So a seismic station has 2 horizontal components and 1 vertical component. So those are the horizontal ones and the vertical one. And then there is a hydrophone, that like pressure gauge, that hydrophone, like kind of underwater microphone trace. And as you can see, or initially when I saw these and when I saw that there's a lot of these in our data, I had no clue what these were, because it's very strong, it's very distinct, it's very repeatable, these signals. But not being a biologist, I had no clue what those signals were. And then, so I spent a few hours researching on this, and I found out that there has been many papers published on something like this. And I found out that those were actually fin whale calls or fin whale songs. I'm not sure, like I have a few sounds here. I'll try to play them to you and let me know if you can't hear anything. So I'll jump over them and let it on you and YouTube to play some of the sounds from the ocean. Can you hear? So this was a humpback whale. And as you could hear, the song is very rich in different frequencies, and it's kind of long and goes up and down. And it's a very fun song to listen. I have two more songs that are a little bit more boring, but maybe more fun from the seismological perspective, and I will tell you why. So this is a fin whale. And you can notice after each of that strong sound or the strong chirp at the beginning, there is an echo that goes up and down. And this is a blue whale, but there's also the fin whale underneath that still. So, okay. I didn't really play the blue whale for you, but the blue whale wasn't as interesting. But the fin whale that you could hear, the second one, it is the sound that I actually recorded in those stations, or that were very abundant recordings at our stations. So as I said, this is a few hours of recording, and that recording that I played to you was 10 times sped up, because those frequencies are very low to be heard and to be played on the regular computer. But if you have a look at these recordings here, each of these peaks in here is one of that call that we could hear, one of that chirp. And then it's about 30 seconds of a break, and then another one, and then 30 seconds and another one. And each half an hour or 20 minutes, there's a little bit longer break, a few minutes, and that's when the whale surfaces and takes a breath. So they call these very regular songs that last for a few hours, and each half an hour they surface and take a breath. So you can also see just from the amplitude in here, this first trace is the vertical trace, and you can see that the amplitudes are getting larger, and then they decrease again. And that is because the whale was approaching the station, so it was getting closer to the station and then swimming away. So a little bit about fin whale. I'm not a biologist, so don't take me up on any of these details, but I'll not go to much of detail. But fin whale is one of the very large whales that has about 23 meters, 75 or 80 feet long. And it has this interesting behavior. There is about 50 to 90 or 100,000 of population around the world. And it has this, and these numbers, they show how many of those whales there are in different locations around the world. It has this interesting behavior that it migrates from the equatorial waters, where it stays throughout the winter, up to the Arctic waters or Antarctic waters to the summer because it feeds and mates up there, I believe. And what's very intriguing about this behavior, or at least in my eyes, is that because winter on the southern and northern hemisphere comes, with that half a year shift, although the whales that migrate on the northern hemisphere and southern hemisphere, they could potentially meet in here because they occupy the same water, they never meet because the winter comes in a different time. So over those years, although they used to be exactly the same species, they developed into slightly different species, because those northern hemisphere fin whales, they mate just among each other, and same for the southern hemisphere ones. So yeah, somehow it's very intriguing for me to realize that although they could meet, they never meet because of that shifted cycle. But back to those calls, the individual calls are about 1 second lasting chirps that are very low frequency at about 20 hertz. So it's probably a little bit lower than what we can hear. Human ear can hear frequencies, I don't know, 40, 50 hertz probably. I don't know exactly, but for us, it's a little bit lower than what we can hear, but they are very, very loud. They say it's up to about 186 or 189 decibels, which is comparable to engines of large ships. So it's one of the loudest sounds in the ocean. And they typically, they start with a frequency that is slightly higher, and then over the duration of 1 second, the frequency drops by about 5 hertz. So in that one song that I showed to you, there were two kinds of calls. There was a high pitch call and a low pitch call. And the high pitch call was about 25 to 20 hertz, and the low pitch call was somewhere about 5 hertz lower than that. So from about 20 hertz down to about 15 hertz. And they are alternating these calls, and it's very, very regular. We recorded, this is an automatic, I made like an automatic detector of those calls, and we recorded many tens of thousands of those calls at our stations. So again, this is a picture of a bathymetry of the Blanco transfer fault, and each of these bubbles is it's in a position of one station, and the size of the bubble is proportional to how many calls we recorded at that station. So the largest bubbles are at about 40,000 calls, and the smallest bubbles are about 5,000 calls. So you can see that each of those stations has recorded many of those whale calls. And for the paper, or for my work, I concentrated on 3 stations, these 3 stations that are labeled with the numbers or labeled with the station ID. And that's because these were stations that had the same seismometer, and also in general, the ocean bottom was very flat. So for the procedure, or for the proof of the concept, what I was trying to show, we needed to have a flat ocean bottom. But before I get to more of the seismology, I will show you one more kind of cool observation. This is on the bottom axis, on the horizontal one. I showed time. So it starts somewhere in fall 2012, and it goes to fall 2013. And on the vertical axis, it's an ID of the station that are ordered in here from the stations that are farthest away from the coast to the ones that are closest to the coast. And with the colors here, I show how many calls there were recorded in those particular periods, or it's a number of whale calls per week. And as you can see, it systematically changes from those sites far away from the coast to those sites close to the coast. And even in here, in the fall of 2013, you can see that again, there's this pattern. It's repeating the pattern, which means that there is some interesting, probably migration pattern of whales that are migrating somewhere between September and May, or maybe they are residing somewhere in here from September till May at those sites that are the closest to the coast, while at the sites that are the farthest away from the coast, the whales are only from January to May. So that's it's rather a biological observation than seismological, but I think that, or it's interesting to see how seismic stations can bring us insights about the biology of whales too. But back to the seismology that I was doing in there, what I did with these calls, I tried to locate where the whales were. So this is a recording, a few seconds, 5 or 6 seconds of a recording of that one call. And besides that direct wave, that is the wave that goes from the whale straight to the station, there was something that I called a waterborne multiple. And it's a wave that travels down to the ocean bottom, it bounces up, it travels on the ocean surface, and again bounces and reaches the station. So we call it a waterborne multiple. And based on this, based on the difference of the times of the arrival between the direct wave and the waterborne wave, we can calculate how far away the whale was away from the station, given that we know how deep the station was and also how deep the whale was. But I will talk a little bit more about that later. So using this method, I located whales or the whale during 6 songs. So that these are those 3 stations that I worked with, and I selected 6 whale songs, and I located the whales as they swam around and over the stations. Taking a little step back, there's a very well-established and very common method in seismology for subsurface imaging, and it's called reflection and refraction survey. It works on a principle that we create some sort of mechanical signal at the surface. And the signal, of course, it travels in the air, and it like if there was another guy standing here, we would hear the sound, but also the sound spreads underneath the surface, like in the geological environment. And when it reaches some kind of an interface, part of the energy gets reflected back and travels back to the surface. And part of the energy actually goes into that interface. So it creates, or into the next layer. So it creates all sorts of reflected waves and refracted waves. And as you can imagine, further away, we can receive those waves that are bounced back to the surface. We can receive them with, or record them in some kind of a receiver. And further away that receiver is, the longer it takes for the wave to reach that receiver. So in here we have receivers at different distances away from the source, and they arrive progressively later and later. And it turns out that this is a hyperbola, like the curve that describes the travel time of a reflected wave. So we don't have to do this only on land, but we do this quite often in the ocean too. And this is one of the primary ways how to image geological structure for oil purposes, because we are trying to find those oil traps, those structures, geological structures that can trap oil. So in oil industry, this is a very common method. So they have these giant ships, and then they are pulling behind the boat, they are pulling these streamers, and those are thousands and thousands of those hydrophones, those receivers, and they create the mechanical signals by these air guns, which looks like this, and it's a chamber of pressurized air that creates this large bubble, and they have series of these air guns, so they create these very strong mechanical signals that then travel through the water column, and they go into the geological environment. They bounce back and forth, and then they are received at these hydrophones, at these streamers in here. And the question I was asking here, We can also do it with the ocean bottom seismometers. So the picture I showed was a boat that was pulling a streamer behind, but we can also record these waves on the ocean bottom seismic stations. But the question I was asking in my research was whether we can just replace the boat with a whale. And it turns out that to a certain level, we can do this because those signals are surprisingly similar in some way. So to show what all kinds of waves I was able to record, so besides the direct wave that traveled straight from the whale to the station, and that multiple wave that was bouncing back and forth, but only in the ocean, there are 4 major kinds of waves that we recorded that were coming from the ground. So the green one was a wave that traveled down to the ocean bottom, and then it penetrated in the ground, bounced from a basaltic basement, which is like the first very sharp interface in the oceanic crust, and it's bounced back to the ocean bottom seismometer. The red one was a similar wave, but it was traveling as a secondary wave. So the difference between, you with a background with physics probably know that in solid medium, we can have 2 kinds of waves. We can have either a longitudinal wave, like a primary wave that the particle vibrates in the direction of where the wave is traveling, and we have secondary wave that there is a direction of where the wave is going, and the particles are vibrating in a perpendicular direction. So this is a wave. Travels through the ground as a secondary wave. Then we have a wave that actually penetrates also the basaltic basement and travels through the basaltic basement and then goes back up to the seismometer. And one more, we have a multiple that goes as a multiple in the water, and then again goes to the basaltic basement and back up. And these waves enable us to constrain the thicknesses and the seismic velocities of those layers. So here I'm showing one of the results, or one of the pictures, like we call it a song getter. So this is a song getter, and it is a little bit hard to imagine what's going on in here, but pretty much the calls are displayed based on the distance between the whale and the station. So in here we have a 0. So this would be if the whale was straight above the station. And as we go further away, we have 1 kilometer, 2 kilometers. So you can see that the closest where the whale was to the station was about 600 meters, roughly. And we display at 600 meters, we display that call. And we do this with every call in the song. So these are a few hundred calls that occurred during that one song at the station BS100. So it's this station in here, and I think it's probably the yellow one. No, I'm sorry, that's the purple one. I have your pictures over the right side of the presentation right now, so I can't see that. So it's a few hundred calls that were recorded during this one song, and as we go farther with the offset, with the distance between the whale and the station, we can notice that there are different like zones of high amplitude, and each of those zones of high amplitude means that there was an arrival of one of those wave groups, and also you can see that these wave groups, or these phases, those zones of high amplitude, they follow hyperbolas. And that's what I was talking about before, that when we have some kind of reflections from, like, either from the ocean or from the subsurface, the travel times, they follow the hyperbolas. So if we actually fit the hyperbolas in there, that's how we can constrain how fast and how deep those layers in the oceanic crust are. So this is just a few of those song getters that I would like to show you. It's definitely, one could stare at it, or I stared at it for weeks and weeks. But so I don't want to bore you to death, because I think it's hard to grasp here during a few minutes. But for example, this is not a hyperbola. This is one of those waves that is not hyperbolic for some reasons, but it's the one that goes down and through the oceanic sediments and travels through the basaltic basements and comes back to the station. And we have a few more. This actually on that very right side. It's very far offset, so it's about 18 kilometers of the distance between the whale and the station, and there is a slight decrease of the slope, and it means that we probably penetrated through this basaltic basement layer into a layer that was one more layer underneath that. So it's coming from very deep in the oceanic crust. And yeah, there's a few more, and it's just like one that this is very interesting. I would like to show you. These were faint ones that I didn't interpret, but those are waves that are traveling actually down to the ocean bottom, up, down, and then into the ground. So those are very complex reflections of that wave. So these are the results from that proof of the concept. So we observed, we could constrain the thickness of the oceanic sediment, and we could constrain the thickness of the basaltic basement, and we could also constrain or estimate the P wave velocity and S wave velocity in the sediment, and the P wave velocity in the basaltic basement and in the lower crust. So these velocities that we estimated in here are actually pretty common for oceanic crust. It's nothing, there's nothing really special, which is kind of good for us, because it would be hard to prove a concept if we were showing some wild results and showing that, you know, this oceanic crust is completely different than something else. So definitely the most important point about our paper was that this is possible to do with whale calls, and we are getting results that are comparable to, or, you know, expectable in the situation like that. But there's definitely a few limitations of this method comparing to air guns. So comparing to that active source seismic reflection. And first is that the whale calls are having a much narrower frequency band. So I don't know how familiar, you are probably familiar with a Fourier analysis, but here, this is these images on the left, and here these two in the middle. They are the time domain recording of the signal. So these are the whale calls, and these are the air guns. And in here, this is how the call looks in the frequency domain. And as you can see, in here we are going from 10 hertz to 100 hertz, and the majority of energy is very sharply located somewhere around 20 hertz, and then it drops out quickly. So we have that signal is really, most of the energy is at about 20 hertz, and it's not, very little is at higher frequencies than that. When we have a look at air guns have the frequency band much broader. So this is from 0 to 150 hertz. And as you can see, it's much broader. So they have both the low frequencies and also the high frequencies, or also something in between. So, and the frequency content defines how deep, and also what resolution of the method is going to be, because the low frequencies, they enable us, they can penetrate deep, and they can give us deep signals, deep reflections. but they cannot really give us the resolution, the high resolution image. Whereas the high frequencies, they cannot penetrate that deep, but in those shallow layers, they can give us very precise image of how it looks like down there. So the whale calls, they can penetrate quite deep, considering the source level, but they cannot really give us high resolution image. So that's definitely one limitation over airgun. Another limitation is that the source level, just the intensity of the sound is limited to those 190 decibels, whereas those air guns, although this is also 190 decibels, we can have 10 of them, we can have 20 of them, and really multiply the energy that goes into the ground. So we can get deeper too. So this is definitely something that is going to limit the method. Another challenge that exists in there is that for the proof of the concept that we showed in the paper, we located the whale from a single station recording, and in order to do that, we had to assume that we know the whale depth, that we know how deep the whale was when it was calling. And we could do that because there are papers that show that actually when the whales are calling, they are not that deep. They are up to about 20 meters deep. And our stations were 3,000 meters deep. They are 3 kilometers deep. So the error was actually quite small. But of course, it introduces some error that we don't know exactly how deep the whale was. So that's one problem. Another problem is that if there is a topography on the ocean bottom, it changes the ray paths. So the waterborne multiple wave travels on different paths. So it changes the trajectory and it changes the time when it arrives to the station. So it also influences and introduces some error in the determination of the whale distance from the station. What we could potentially do about this, we could adopt a slightly more complex method of location of the whale. So instead of using one station, we could use multiple stations, and then we don't care how deep the whale was, or we do, but we can find out, we can calculate that from multiple stations. We also don't use any reflections, so we don't really care about the topography of the ocean bottom. So this would be definitely a way around it, which would help us, but it would be a little bit more complex, and it was beyond the scope of the study that I was presenting. Another thing, maybe like in future, there are like more things that you'll probably ask me about. So I moved some of those a few slides in that like questions section. But one more thing that I wanted to talk about is that this is kind of a new thing, using fiber optic cables as seismometers, because it turns out that we can use fiber optic cables to record ground motion. So in fiber optic cables, there are some heterogeneities distributed in the whole cables, and if we send a signal in there, we can sense quite exactly how the heterogeneities are reflecting the signal back. So if we send the signal in, and we can record those backscattered signals, and if the cable is undergoing some deformation, it gives us, we can record in time how those we can pretty much record the motion of the cable. So this is one way that we could probably try, and that would be extremely useful to have a recording like this from the ocean bottom of the whale songs, because we would not have only one station sitting on the ocean bottom, but we would have pretty much, on a 3 kilometer long cable, we would have 3,000 of those stations. So that would be, that would definitely, that would be a different level of processing. That would help it a lot. And also, I don't think that actually seismology and subsurface imaging is the only possible application of those whale calls, because whale calls have been used extensively for studying whales themselves in the past 30, 40 years. But what this paper, or what our paper shows, is that maybe there's more information in those calls than we previously thought there is. Maybe, you know, every sound like carries information about the source. It carries the source information about me, what I'm actually saying. It also somehow changes with the recorder. Like if you hear me talking, it also, you know, somehow the sound like interferes with your ear and stuff like that. So it also carries some information, or has some information about the receiver, but it also has some information about the travel path, about the medium where it was traveling. So I sound differently when I'm talking in the air, and if I was shouting underneath the water, it would sound differently. And the room where I'm sitting influences how my voice sounds like, because there's all of those echoes in the room. So it's not only the direct wave that travels in the computer from my head or from my mouth, but there's also all kinds of echoes from around the room. And it's the same with whales. Like there's much more information, and it's only about learning how to, like, having ideas about what we want to learn from those sounds, and how to extract those sounds, and how to extract those informations from the sounds. So I think what I'm like, on one level, on the first level, I was trying to show that whales can be used for subsurface imaging, or the whale sounds can be used for subsurface imaging. But on a different level, I was trying to show that maybe we can think about some other applications, and maybe someone else will be like, oh, like I don't understand seismology, but I understand, you know, I'm an oceanographer or something like that, and I want to use it for, I don't know, ocean water tomography, for like finding out slight variation in the ocean water velocities, because that's what people do. Or, you know, pretty much anything. I think that there might be more into it. Maybe not. Maybe I'm wrong. But I'm interested whether, or I'm curious whether somebody will pick this up and say, hey, what they showed is cool, but I have a better idea what to do with this. So yeah, that's kind of maybe a deeper, on the deeper level, what the paper is showing. So in conclusion, the whale calls are abundant and strong and globally available when it comes to fin whales. And yeah, we can use them for seismology. And I would like to acknowledge the whole team, because there are many people involved collecting the seismic data. My former advisor, John Nabelek and Jochen Braunmiller, and the crews of those research vessels, Melville and Oceanus, and all the volunteers and technicians that were involved in this. And I would like to thank you for your attention, and really my honor to be invited over, and yeah, and being able to talk to you about my science.
Yeah, thank you for being able to speak with us. I thought this presentation was really really good looking as well. Like you designed it so well. I really like the last point you made about how your research is there to inspire other research too. Like they can take portions from it and say like, hey, why don't we do this for a new thing? I think that's like the research spirit, right? So
Yeah, I think so. Yeah.
yeah, yeah. So now we're gonna progress into the second portion of the talk, which is um, asking you some questions and um, trying to see your learning from your expertise in this field. Um, what other faults other than the Blanco transform fault are you interested in studying, and um, what kinds of future research topics are you interested in?
I'm not working on whales and the ocean bottom seismic data anymore. I'm working on data on land, and we are trying to, there is like an open source project which tries to develop a low cost earthquake early warning. I don't know some of you might be familiar with earthquake early warning. You probably would be if you were living in California, maybe not in Boston, but maybe you are. So pretty much like the basic idea behind that is that we can record earthquakes at its very beginning. So when a large earthquake happens, it takes a few minutes for the whole rupture to go through. So if we record the earthquake at its very beginning and we estimate how strong it's likely going to be, we can send signals to places, or we can send alert to places where the shaking hasn't reached yet, and we can give them a few seconds or tens of seconds of an alert, and people can seek cover or run out of a building that would otherwise fall on their head. So, and these systems, they exist, but they are many of them are based, or few of them are based on these very expensive instruments, those that I was showing in the first part of the presentation. So it then takes millions and millions of dollars to establish these systems. And what we are trying to do with a team of people, we are trying to use cheap accelerometers, very similar to those that you have in cell phones. So we are trying to use them for such a system. So we could make a system that is in the order of tens of $1,000s, or not tens of millions of dollars. So it's based on the principle of IoT. So we are sending data in real time through IoT infrastructure like MQTT and stuff like that. And then we use cloud services for computation. So that's what I'm working on. We are trying to test the system in a few places. My region is Nepal, so I am trying to establish such a system and test the system in Nepal. So that's the main project I'm involved in. If in the future I have more opportunities to working with whales, I would have a few ideas where to take it further. So I wouldn't be against, but right now I don't have funding for whales, so that will have to stay on the back burner for a little while.
I see. What exact kind of, how do you make it as accurate even though it's cheaper technology?
I'm sorry, what was it? How do we make it as accurate?
Yeah, even though it's cheaper.
So the thing is that those large earthquakes that we are interested in, they are so strong that we can record them quite easily with low-cost sensors. So when we are interested in very small earthquakes like those that I was studying on the Blanco transfer fault, we could not use anything cheaper than what we used. So the really high-end, very expensive sensors definitely need to be used in situations when you are trying to record small seismic events or like very precisely to record something. But when a magnitude 8 comes, it's a very, very strong shaking. And you don't need to have a tens of $1,000s instrument to record it. Like your phone will record it very well. And actually there is a technology that uses or tries to use the data from accelerometers from the phones too. So for those, but it has also like its own challenges because you carry it in the pocket and you jump around. So
Yeah,
it is possible. So yeah, it does not need to be as precise when it comes to earthquake early warning. It needs to be precise when it comes to research seismology and very small earthquakes.
I see. Now some specific questions on your talk. Um, you said that the changing seafloor bathymetry, if that's how you pronounce it, right? That influences the source station distance determination. This is from your article. And so you're saying that if it's not generally really flat, it'll vary, and you can't really measure that as well. How how do you think advancements would in technology would help you measure these rougher areas? And um, you said we could use machine learning algorithms such as deep neural networks to use this for automatic whale detection and also processing their songs. Would you dive more into that?
Yeah, for sure. I actually have a few simple slides on this because I knew about the question. So I see two major areas where we can apply machine learning, and I think they're in this task. And I am sure that there may be many more that I can't see straight away. But straight away, I can say that we can use it for detection of the signals, because the signals are very similar, and we have very good using convolutional neural networks. We have very good experience in in earthquake detection, and earthquakes are much harder to detect than these whales. So we could probably quite easily teach a convolutional neural network for detecting the direct wave. I'm not sure if we could teach it to detect some like later lower amplitude waves. I think it would be more difficult. But for detection of these and very precise detection, I think that would be very useful. But what it would be maybe even more useful, and that's to your question, how it would help us to deal with that bathymetry problem, is that we can teach it to identify the same calls, or we can do the detection at multiple stations at the same time, and the algorithm can affiliate those individual detections and find out whether it was from a common source, if it was one whale, and in case that it was, it can locate the whale. So we can, for example, we can create like how we can teach the algorithm. Either we can teach it on the whales that we already found and did this work with hand, or we can just introduce some um, synthetic data. We can model these synthetically and then teach the deep neural network for recognition the patterns. So for example, if the whale is here, the signal at the station 1 is coming at this time, the signal at station 2 is coming at this time, this time, this time. So, and this pattern can be recognized by a deep neural network. So this, we call it in seismology association of the detections into like an event, which is like one single whale calling. So that can definitely help us. But yeah, this is how I see the machine learning to be helpful on the first level. But I'm sure that there are more clever people out there when it comes to machine learning than I am, so people can see much more probably.
Sorry, I was on mute. I'm excited to see the new advancements in uh, this technology. Um, in the ending of your paper, you said that fin whales seem to have a narrower frequency band, lower dominant frequency. Do you have any plans to conduct research using other whale songs and calls? Maybe not only whales, maybe uh, like killer whales, orcas with the clicks or different distinct types of sounds. Do you think this would help assist in seismic studies?
It's a very interesting question, and I was thinking about one particle whale, which is a sperm whale. And the sperm whale, it produces sounds that are even stronger and much broader frequency bands. So it goes from a few kilohertz to over 20 kilohertz. So these clicks, they are very sharp, and these clicks are very loud and very broadband. They could they would not penetrate as deep as fin whale calls, but for that very shallow layer of sediment, I think that could be useful. The processing would be probably quite a bit different. I don't really know how exactly that would work, but I think that there would be some information from the subsurface, from that like shallow subsurface. So I would be very interested in trying to process some of these signals. Unfortunately, our stations were configured to record signals of 50 hertz and lower, so we don't have any sperm whales, and I don't even know honestly if there are some sperm whales in that region or not. But for sure, we did not record any. But on the other hand, I'm sure that many stations out there, for example, deployed for oil and stuff, they did record many of these. So if I had funding for this, of course, I would be very interested into going out there and either trying to capture some of these signals or using some data that has been recorded already to try to figure out how to extract that information from here. And when it comes to other sounds in the ocean, as you suggested, I think I haven't really studied any other ones, and I don't really have a deep understanding of like how those sounds are structured, how like what frequencies they are in and stuff. But yeah, I think that out there are people who understand them much better and may have all these ideas, like if it can be used. I think, and to the second part of your question, I'm not really sure if I'm quite sure that fin whales cannot be used as a substitute for air guns, unfortunately, because air guns are stronger and broader frequency band. And I'm not really sure whether whales or any kinds of sounds in the ocean, like animal sounds, I don't think that none of them can replace air gun surveys. I think that they can be a useful complement for our research and stuff, but I would be skeptical towards full replacement. I don't think that that would be possible. I think that maybe in the future we can learn how to process air gun signals better, so we don't need to make them as loud. Maybe we can like gain more information from a slightly less of a signal, but I don't think that those animals can really replace those air guns.
I see. So I'm gonna ask two last general questions since we're running out of time a little bit. So how do you say you overcome challenges and hardships in your work when things aren't working as you visualized, as you expected? What specific steps do you take to advance your research even though things are not going well?
I was thinking about this question. It's a tough one, and I think that like my recipe, I can't like really teach anybody, and like, but I think that even when things are going badly or not really progressing, I think doing at least a little bit, maybe you don't always need to be enthusiastic about your work and like working 10, 15 hours a day. Like, yeah, sometimes when you are really stoked about the problem that you want to crack, that's what you do, like, because you really like the thing that you are doing. But oftentimes, like I had this during my PhD quite a bit, like it's a long thing and you have downs and you have ups and downs. And like, but even though you don't feel enthusiastic or you feel down or something, I think it's quite important to do just a little bit to keep like progressing a tiny bit, like,
I see.
because that's the way that opens up like new ways and like shows the solutions eventually. But I think that, yeah, that feeling, sometimes I have a feeling that if I am not like working a lot, like there is no meaning in it. But I don't think that's the case. I think that even if you are doing just a little bit, you are still like progressing somewhere, and like the new pathways may open up, and they often do. So just, yeah, keep going a little bit at least, and then the pace will pick up eventually again.
I see. And based on all your experience with your research taking you all over the world, what top 3 tips would you give someone in college whose ultimate aim is looking for new discoveries, products, and ideas, and making these to improve the world?
Another tough question. Like first, that is kind of more practical. I'm sure that you guys are probably know this better than I do, but machine learning is going to be everywhere in 10 years. It's everywhere now, but you definitely need to do it in technical fields. And your expertise or my seismological expertise is always going to be needed to apply those machine learning algorithms. But you need to be able to do them, or at least understand them on some level that you can explain somebody who really specializes in machine learning what you need. But that's really going to be everywhere. So I think that that's something that like that train, I felt like when I was on my PhD, and I haven't done that. And then I went out in the world. I found out that there's much more of it than I previously thought already, because in 5 years when I didn't do that, like it has progressed a lot. So I think that this is one advice for sure. And then another advice, like if somebody wants to, as you said, like make some progress or discoveries and something like that, I think just being curious, like it's really important to maybe sometimes knowing less is better than knowing more, because that can take you to solutions that you haven't, like sometimes I think that like too much of reading and too much of knowing how things are being done can limit you in your creativity. And I think that you should always, if you are interested, like you should always take your time, take an afternoon or take a week of like trying, like digging in an option that you find yourself curious about. And like because 99 out of 100 won't work because somebody else have probably tried it, or or not, but it's not gonna work. But that curiosity and the time that you sidetrack from your main project, I think that's you may eventually hit something that really works. And yeah, that would probably be my advice. Like, yeah, be curious about things, and even things that don't seem there is much about them, everything has something very interesting in it, like when you look at it closely enough. And yeah.
Yeah, that's good advice. So like diving into something, and then as you keep on diving in, you start to get obsessed with it, right? And you feel like it's drawing you in even more.
Yeah, like I have tried many things that didn't work. I mean, when I was procrastinating on my PhD, I used our seismic data to try to find, North Korea nuclear tests and stuff like that. And, none of it worked, but the whales worked eventually. So
Yeah,
I think it's important, and everything teaches you something, like even when the thing that you try to do it doesn't work eventually, but it taught you something. So I think it's important to go these ways that are probably not very likely to work. But that's kind of how I like did the whales, like because it was a new perspective on something, and I gave it a few days just to like try it for myself if the data is there or not, and it turned out to be there. So yeah.
yeah, awesome. Yeah, thank you for taking the time to talk to us.
Thank you so much. That was very informative.
Thanks for having me. It was my honor, guys and girls. Sorry.
So I know I'll definitely be reaching out to you with more questions and on your studies. What is the best where should we find you? Where should the audience find you?
Email is probably the best. So I don't know if you will share my email with the audience, or I've LinkedIn, and yeah, well, email.